Imagine a radio station. The DJ is broadcasting music. She doesn't know how many listeners are tuned in. She doesn't send music to specific listeners. She broadcasts to a channel, and anyone who is tuned to that channel receives it. When a new listener tunes in, the DJ doesn't need to do anything different. When a listener tunes out, same. The DJ and the listeners are completely decoupled. This is the publish-subscribe pattern, usually shortened to pub/sub. Publishers send messages to a named topic or channel without knowing who the subscribers are. Subscribers express interest in topics and receive messages when they arrive, without knowing who published them. The messaging infrastructure handles routing between the two. Pub/sub is the pattern that enables truly loose coupling in distributed systems. Adding a new consumer of an event requires no changes to the publisher. Removing a consumer requires no changes to the publisher. Consumers can come and go independently. The classic implementation exercise in the book is a real-time chat application using WebSockets. WebSockets provide a persistent, bidirectional connection between a browser and a server, enabling real-time push communication. The WS library in Node.js makes building a WebSocket server straightforward. You handle the upgrade from HTTP to WebSocket, then send and receive messages on the connection object. The chat app is simple: client connects, sends a message, server broadcasts it to all connected clients. Within a single Node.js process, this works perfectly. The server maintains a set of all connected WebSocket clients and iterates over them to broadcast. But then the scaling problem arrives. And it reveals exactly why pub/sub infrastructure, not just in-process broadcasting, is necessary for production real-time applications. Your chat application works beautifully on a single server. You scale it up, 2 servers behind a load balancer because traffic has grown. And suddenly, chat is broken. User Alice connects to server 1. User Bob connects to server 2. Alice sends a message. Server 1 receives it and broadcasts to all clients connected to server 1. Bob is on server 2. Bob never sees Alice's message. This is not a bug in your WebSocket code. It's a fundamental architectural problem. Your server's state, the set of connected clients, exists only on that specific server instance. Multiple instances can't share in-process state. The solution is to move the pub/sub infrastructure out of the Node.js process and into a shared external system. Redis pub/sub is the standard choice for this at small to medium scale. Redis pub/sub is exactly what it sounds like. Redis has 2 commands. Publish sends a message to a named channel. Subscribe registers interest in one or more channels. All subscribers to a channel receive every published message. In the multi-server chat architecture, when Alice sends a message to server 1 publishes that message to a Redis channel, let's call it global chat. Both server 1 and server 2 have subscribed to that channel. Redis delivers the message to both. Server 2 receives it and broadcasts to all its connected clients, including Bob. Bob sees Alice's message. The key insight: Redis becomes the coordination layer between all your server instances. It's the pub/sub broker that spans process boundaries. Each server is both a publisher and a subscriber. Messages flow, client to server to Redis to all servers to all clients. This pattern extends beyond chat to any real-time feature that needs to work across multiple server instances: live collaborative editing, real-time dashboards, multiplayer games, live notifications. Redis pub/sub is the lightweight solution. For higher scale, Kafka provides the same pattern with better throughput and message persistence. Redis pub/sub adds a broker and infrastructure component you must run, monitor, and keep available. For very high performance or fully self-contained use cases, there's an alternative: peer-to-peer pub/sub using ZeroMQ, with no central broker at all. ZeroMQ is a messaging library, not a messaging server. There's no ZeroMQ process to run. You link the library into your application and use its socket abstractions directly. ZeroMQ handles connection management, message framing, and routing internally. ZeroMQ provides a PUB socket and a SUB socket. A process with a PUB socket binds to a network address and publishes messages. Any number of processes with SUB sockets can connect to that address and subscribe to receive messages. Each SUB socket can specify a topic prefix to filter messages. It only receives messages whose content starts with that prefix. The architecture for a brokerless chat server cluster: each server instance has both a PUB socket, to publish received messages, and a SUB socket, subscribed to all other servers' PUB sockets. When Alice sends a message to server 1 publishes it on its PUB socket. Servers 2 and 3 have subscribed to server 1's PUB socket, so they receive it immediately and broadcast to their connected clients. This requires each server to know the addresses of all other servers, which is why service discovery, from the previous chapter, pairs naturally with this pattern. When a new server instance starts, it registers with the service registry, and all existing servers add its PUB socket address to their SUB connections. The performance advantage is significant. ZeroMQ's messaging latency is in the microseconds. There's no broker bottleneck. The trade-off is operational complexity, no central place to monitor message flows, no built-in message persistence, and topology management must be handled by your own code. For performance-critical, ephemeral messaging where you can tolerate message loss, ZeroMQ's brokerless model is compelling. Let's zoom out and look at pub/sub as an architectural pattern in production systems, because the specific chat example scales to cover a wide range of real-world use cases. Redis pub/sub is the workhorse for most production real-time Node.js applications. Socket.io, the most widely used Node.js real-time library, has a first-class Redis adapter, the Socket.io Redis package. When you enable it, Socket.io automatically uses Redis pub/sub for cross-instance coordination. You write your application code for a single instance, and the Redis adapter transparently handles the multi-instance broadcast logic. The scaling story becomes, add Node.js instances, point them all at the same Redis cluster, and cross-instance broadcasting works automatically. Kafka is the choice when you need pub/sub with durability. Events aren't just delivered in real time, they're also persisted on disk for a configurable retention period. A subscriber that was offline comes back up and can replay all the events it missed. This is the foundation of event sourcing architectures. It's also why Kafka is used for audit trails and compliance use cases where you need a complete immutable record of every event. The broader design principle at work across all these pub/sub implementations is the observer pattern from the Gang of Four, applied at the infrastructure level. In-process observer, objects register callbacks. Cross-process observer, services subscribe to topics. Cross-data center observer, Kafka with geo-replication. The same pattern, applied at larger and larger scales. The pub/sub pattern also has a natural affinity with event-driven architectures. When your services communicate primarily through events rather than direct synchronous calls, each service becomes independently deployable, independently scalable, and resilient to failures of other services. Pub/sub infrastructure is the plumbing that makes event-driven architecture operational rather than theoretical.